And now we have the last part of our discussion on the topic of temperature and heat. We have examples part 3. So we have sample problem number 5. A copper slab of length 15 centimeters and cross-section area 105 centimeters squared has TH 125 degrees Celsius and temperature TC 10 degrees Celsius. How much heat is conducted through it in 30 seconds? The conductivity of copper is given 400 watts per meter Kelvin. This example is pretty much straightforward. The copper slab, the length is given. Let that be L, 15 centimeters. Convert to meters. You have 0.15 meters. The cross-section area is given 105 centimeters squared. Let that be cross-section area A, equivalent to 0.0105 square meters. Elapsed time or total time is given 30 seconds. So T is equal to 30 seconds. And the temperatures TH and TC, the hot temperature and the cold temperature, or the higher temperature and the lower temperature, are both given. TH is 125 degrees Celsius, convert to Kelvin. TC is 10 degrees Celsius, likewise convert to Kelvin. So you have 378.15 Kelvin and 283.15 Kelvin. Lastly, the conductivity of copper is provided. Let that be K. K is equal to 401 watts per meter Kelvin. We are looking for how much heat is conducted through the copper slab in 30 seconds. We are looking for total heat transferred, Q. Now, this is solid copper slab. So we have thermal conduction or heat conduction. H average is equal to Ka TH minus TC over L. And our general equation for heat transfer rate, H average is equal to Q over T. So Q over T is equal to Ka TH minus TC over L. We know elapsed time T. We know K. We know cross-section area A. We know TH and we know TC. Lastly, we have L, length of the copper slab. Completo. The only unknown is the total heat transferred Q. So isolate Q. Q is equal to KAT, TH minus TC over L. Plot in the values. And you are able to calculate the total heat conducted through the copper slab. Q is equal to 96,841.500 joules. Pretty straightforward solution. Direct application of the heat conduction equation. And finally, we have sample problem number 6. Consider the figure of a cross-section of a wall showing 4 layers of materials. You have a cross-section of a wall, 4 layers of materials. You have material Ka, material Kb, material Kc, and material Kd. The first material, Ka, has a thickness of La, Kb has a thickness of Lb, Kc has a thickness of Lc, and Kd has a thickness of Ld. This side of Ka has temperature T1. The interface between Ka and Kb has interface temperature T2. The interface between Kb and Kc has interface temperature T3. And the interface between Kc and Kd has interface temperature T4. And this side of the wall, the other side of the wall, has temperature T5. The problem compares LD with LA. LD is twice LA. It compares material conductivity of material Kd and material Ka. Kd is 5 Ka. Temperature T1 is given 25 degrees Celsius. Temperature T2 is given 20 degrees Celsius. And the temperature T5 is also provided negative 10 degrees Celsius. Determine the temperature T4, the temperature on this interface between Kc and Kd. So, we have LD is equal to 2La, Kd is 5 Ka, temperature T1 is provided, 25 degrees Celsius. Convert to Kelvin. Temperature T2 is also given, 20 degrees Celsius. Convert to Kelvin. And temperature T5 is given, negative 10 degrees Celsius. Convert to Kelvin. We are being asked for temperature T4. This is a wall. On this side, you have temperature T1, 25 degrees Celsius. On the other side of the wall, temperature T5, negative 10 degrees Celsius. So, T1 is greater than T5. So, T1 is TH and T5 is TC. Heat will flow from hot to cold, from higher temperature to lower temperature. So, heat will flow from left to right. That's also the direction of our heat rate flow. That's also the direction of H. Since this is just one wall, each layer has the same cross-section area. So, AA is equal to AB is equal to AC is equal to AD is equal to A. So, let's just use cross-section area A for all the layers. This is a solid wall, solid material, thermal conduction analysis. And for materials that are in series connection or layering, there's only one heat transfer rate flowing through the object, flowing through the layers. H average is equal to HA, is equal to HB, is equal to HC, is equal to HD. Clearly, the problem is comparing layer D, material D, with layer A, material A. So let's do the same thing for our heat transfer rates. Let's compare HA with HD. HA is equal to HD. Conduction, therefore H is equal to Ka, TH minus TC over L. For HA, that will give you Ka, A, T1 minus T2 over LA. Thickness or length LA, thermal conductivity Ka, cross-section area A, and TH is T1, TC is T2. So, KAA, T1 minus T2 over LA. Doing the same thing for HD, we have KDA, T4 minus T5 over LD. We can cancel out cross-section area A. KD is 5KA, so replace KD by 5KA. LD is 2LA, so replace LD by 2LA, which means we can cancel out KA and we can cancel out LA, leaving us with T1 minus T2 is equal to 5T4 minus 5T5 over 2. Looking at the known values for the temperature, we know T1, we know T2, we know T5. The only unknown is T4, so isolating T4 and plotting in the values, we are able to calculate T4 to be 265.150 Kelvin or negative 8.000 degrees Celsius. And that's it for our discussion on temperature and heat. Thank you for watching.